printed circuit boards. For the printed circuit boards, we divided them into sort of like two different systems. One board, which is a main board that goes on the back of the wear, which provides all the power, has a battery connected to it. It's encased. It has the radio on it. It has the microcontroller on it. We put all the voltage regulation. Everything is on that single board. And then we have smaller individual boards that interface these sensors with the microcontroller. Those are mostly just analog boards with buffers and amplifiers and comparators. We have one for the respiratory rate sensor, one for the thermistor. Those are also encased. And also we have another, a smaller board which has the emergency state indicators, which that's for the user, so the user knows if there's something wrong, you know, with his health. The emergency indicators can either be LEDs, a buzzer, or a vibrating motor. And that all depends on the application. Whether it's someone in combat, you probably don't want something, you know, making a lot of noise. You probably want the vibration thing, or you know, the different things for different users. Next slide, please. And here, this is an amplified image of our board. This is our main board. This provides all the power. You can see the microcontroller up top. Under that is the accelerometer, and that's our radio on there. And next is Jesse's going to talk about the communications.
All right, since the smart vest will be using commercial off-the-shelf devices, they have to be able to communicate to the microcontroller. Components such as the accelerometer that measures or that relates body position sends out an analog data to the microcontroller, and it's within the tolerance of the microcontroller itself. XPOD's pulse oximeter that will give us pulse rate and blood oxygen level sends out a digital signal that is far higher intolerant, or a far higher voltage level than what the microcontroller can tolerate. This has to be a voltage level shifted down in order so the microcontroller does not get damaged by the sensor. Power consumption is also a major concern for us since the vest will be relying on a battery pack. At first, our transceiver radio, which actually pulls 730 milliamps of power in order to produce 1 watt, to transmit at 1 watt. At first, I believe that was going to be the heavy power consumer, but since the low data rate that we'll be sending at, actually the microcontroller, which actually uses 120 milliamps constantly, end up being the major power consumer for our vest system. LG?
So the transceiver is a part of our network infrastructure. We purchased 2 radios, 2 DigiExtend radios operated at 900 megahertz. For our range, our goal is to maintain a line of sight of 1 kilometer, which is about 0.62 miles. For our actual range testing, we tested up to 1.6 kilometers, which is equivalent to about 1 mile. We could have gone farther than that, but due to our testing environment, we met our goal. So we stopped at that exact point. So basically, what the radio is in charge of is it takes data from the microcontroller, sends it wirelessly over to the GUI, and CJ is going to talk more in depth about the microcontroller.
At the heart of the vest is a microcontroller. For this project, we picked the Netburner Mod 5213. It's a 32-bit microcontroller, and it's got 8 AD channels and 33 GPIO pins that we were able to use for this project. The tasks of the microcontroller were divided into 2 sections. One was talking to all the sensors, and the other was talking to the command station through the radio transceiver. Now the sensors were mostly interfaced through an analog to digital converter, except for the pulse oximeter, which uses a serial method for communication. The radio also was interfaced through serial, and all the data sent to the radio was sent back to the command station. And to the microcontroller, the radio is invisible, so it's just as if there was a serial port going directly to the command station. As we talk about the command station, here's Sean.
The main function of the command station is to gather data from the smart vest, process that data, and then display it to an operator who can assess a user's state of health. It has 3 main features in which in order to help the operator do that. First is to create and edit user profiles, those who will be wearing the vest. Because each individual is different, the command station needs to estimate their limits. It can also show a multi-user general overview and a single-user detailed overview to make more accurate assessments. And in case the smart vest user goes out of the range of the command station has an algorithm to automatically reestablish connection to the smart vest in case it comes back in range. Next slide, please. This is what the command station software looks like. This is the overview. You can see there's 4 profiles, and their stats you can see at a glance. If someone has their state is not normal, their box will flash a certain color. In this case, this person, he's in the critical health state. That means someone needs to go and see him immediately. Down here is a profile editor, and if you click on the details button, it'll bring up a more detailed version, which these gauges will show you the limits of each person's vital signs. History of the vital signs for 5 minutes, and if particular vital signs are irregular, it'll flash a certain color. In this case, it's yellow. They are cautioned you should watch it, but they're not in any immediate danger. It also features a tabbed interface. That way, instead of going back to the overview window, click on each person's detail button, you can just click on the name of the tab and it'll show you that person's details. And this is the algorithm that the command station uses to maintain communication with the vest. On top, in this yellow, is initialization, where the command station pings for vest and then sends profile data, which will come in handy later. It'll go to the screens area, which is the main loop. The command station requests data, the vest sends it, the command station processes it before requesting again. This happens in about a second. If the vest user goes out of the range, we have communication failure. The vest can become autonomous using and it can do basic calculations using the profile data was sent earlier as the vest command station tries to reestablish connection to the vest. And to talk about our product development history is Michael.
Thank you. The project development is comprised of several stages throughout the semester. From weeks 1 through 5, the first 4 weeks of our semester included the sensor research and the placement of the orders for this sensor. Once we had the devices ready, we started writing code for the GUI, the microcontroller sensor interface, the PCB and prototype hardware, the radio network infrastructure, and integrating all of these devices into the vest. And for the last 2 weeks, we've been doing testing of our system, and we're just making final adjustments. So we expect to see you this coming Friday, so you can enjoy it for final product.
For the project completed, the expenses go as follows. In green, you'll see that we spent the majority of our money at the software side, about $2,600. Moving on to the radio, where we spent about $860. We bought another radio just in case if something were to happen. Next, you'll see here in blue is the sensor side, which includes the thermistor, the accelerometers, and the multiple respiratory sensors that Marco had mentioned earlier, and the pulse oximeter, which cost about $780. And then lastly, in purple, the miscellaneous portion, it is about $450, which includes the vest material, those small parts for the PCB, and USB serial ports. In total, the project costs about $4,700. For the BIB system, we would like to market this product to the civilians and government agencies. The potential vest product price ranges at around $1,700, and the potential command station, including the radio to communicate with the vest, is at around $400. For the labor, we concluded it would be $30 an hour, 80 hours for 1 month, and then 4 months to complete by 12 engineers, to total at $115,200. This doesn't include health insurance, dental, 401k that's normally included in employee package. And now on to Robert to conclude the presentation.
Alright, let me remind you that our system is to remotely monitor vital signs. So that can mean someone's father, mother, brother, and sister. We're here to save them in the burning building, in the battlefields, and in the cities. Other applications, of course, in the military, the government, like the presidents, hazardous areas like miners, and athletics, like possibly like football. We would like to thank Dr. Tamala and John Kennedy. We came into this project as brittle engineers composed of many elements, but like a blacksmith, they have hardened us as steel engineers, known from SDSU. We would like to thank our sponsors, Cubic Corporation, Kevin Priest. Your money and endorsements have guided us, supported us, and we thank you for that, sir. And we would like to finally thank the faculty and staff. We came here as small students who wanted to learn from you, and you have guided us throughout the years, and we thank you for that golden knowledge. Now I'm sure we have impacted your auditory sensors. Now let us visualize a scenario. Here we have a video scenario of what we're going to do on demonstration day. Hopefully it's shiny, so let's play the video.
I see 3 hostiles and 1 hostage, over.